So this is a mandatory disclaimer. Yeah. So the image quality is the delicate balance between all these options what you're seeing on the monitor. So it's a balancing of the SNR, CNR, or contrast to noise ratio, and the scan time and the spatial resolution. It's important to the operator or the radiologist or the technologist whoever is operating the scanner having a good knowledge of these parameters to obtain very good IQ. Or simply the scan parameters optimization, I can say that to obtain or generate an image with good resolution, with acceptable scan time, and without any artifacts. We'll just see all these parameters one by one. So first we'll talk about the SNR or the signal to noise ratio. So this word you may hear in your daily clinical practice, SNR. What is this? Signal to noise ratio. This value is influence the quality of the images. Suppose if the SNR is low, we can say that the images are grainy. And if the images are grainy, it is very difficult the radiologist to diagnose the diseases. So it is mandatory that we are obtaining images has sufficient amount of SNR and a sufficient spatial resolution within the acceptable scan time to obtain very good images. So in this formula, the MR image, the SNR will be specified these parameters. So over here you can see this for the 2D images, and this is for the 3D images. We'll see after changing these parameters what's really going to happen, actually going to happen. Okay, so not only these parameters, there are some other parameters also affecting the FOV SNR directly. So the first thing is a magnetic strength. So this is just for the illustration. You can see there are two images of the brain, one acquired in a 3 Tesla scanner and other acquired in the 7 Tesla scanner. You can see the first image is a bit grainy, means the SNR is low. The second image, there is no graininess, that means the SNR is higher. And the images is diagnostic, you can see. So what's happening if you are increasing your field strength? So just go back to the old school. So once the patient is inside your bore, you can two types of proton alignments according to the different energy states. One will align parallel to the main magnetic field. You can say it is a low energy state protons, and the one which are a bit stronger and they don't want to align along the main magnetic field, we can say it is an anti-parallel state protons or high energy protons. If you are increasing your magnetic field, the anti-parallel or the high energy protons, quantity of these protons will be reduced. So you will have a more number of parallelly aligned protons, thus contributing your MR signal. So that means higher strength magnet, you will have more protons to produce the signal. That means you have high SNR and high magnetic field MR. Next is the proton density. So you can see two voxels. The voxel is a volume element, the image. So you can see in the first box or the first voxel, the number of protons are less. So thus the overall signal is less compared to the second voxel, means it has large amount of protons producing large amount of signal compared to the first voxel. The low proton density, the signal will be low, SNR will be low. With high proton density, the signal will be high, overall the SNR also will be high. So we can see the relationship between the few of these and parameters First we'll think about the SNR and the slice thickness. So the voxel thickness or the voxel volume directly proportional to the slice thickness scanning FOV and the matrix, that means the frequency and the phase matrix. So over here you can see the first image is scanned with a 10 mm slice thickness, and the third image scanned with a 2 mm slice thickness. So you can see the first image are smoother, that means there is no graininess, that means we have a very good SNR. And the last image, not very smooth, and it has a good graininess, that means the SNR is better. So the SNR is directly proportional to the slice thickness. So slice thickness increases, SNR increases, slice thickness reduces, SNR also will reduce. So here, there is one more word you can see over here is a spatial resolution. We'll discuss about what is spatial resolution. So as the SNR, as the slice thickness increases, you can say the spatial resolution is decreased. You can see there is not much gray and white matter differentiation. This image. But if you see in the 2 mm slice thickness, we can see the better gray white matter differentiation. So the spatial resolution means it's the ability to distinguish between two separate tissues. Okay, so we'll discuss. So just assume we have a 4x4 matrix image. So you can see the slice thickness is large, or the voxel is bigger. It can accommodate more number of protons. That means you will get more SNR. I just reduce the slice thickness. You can say that just reduce the slice thickness into half. So the voxel volume is reduced, and the number of protons in each voxel also reduced. That means signal is less, SNR is less. So you can see the linear relationship between the slice thickness and the SNR. So the 10 mm slice, the SNR is 1, and if I am reducing it to half, the SNR also half. So what is partial volume effect? So in MR image, okay, just assume that this is a 10 mm slice thickness. It has two separate tissues. It has two different signal intensities. Suppose my slice thickness is thicker, that means a 10 centimeter. These two signals will be averaged, and you cannot distinguish these two structures separately. That's called the partial volume effect. So if you scan in 10 mm, it will be like this. But if you scan in 5 mm slice thickness, you can easily distinguish these two structures or these two signals separately. So that means increasing the slice thickness, the more partial volume effect. Reducing the slice thickness, partial volume will be less. Simple. Let's see how it will happen if you change the field of view. So it is proportional to the square of the FOV. So this is a 24 centimeter FOV. All other scanning parameters are constant. And here you can see this is a 14 centimeter FOV. So the first image, the images are very smoother and the edges are blurred out. It's not very sharp. That means the spatial resolution is less. But in this case, the 14 centimeter FOV, you can see the edges are very sharper. Means you have a very good spatial resolution. And it is a simple thing. If you want to increase your spatial resolution, you can just reducing your FOV. Make an eye on your SNR also. It should not be reduced. Okay, so what will happen if you already change your FOV? So small FOV, the voxel volume is less, as I told earlier, and the larger FOV, the voxel volume is larger, can accommodate more number of protons. So yes and no. So this is the relationship 0 SNR. As I am increasing the FOV, the SNR also increasing, and we can calculate the voxel size easily to maintaining or obtaining a good SNR images. So this is the mathematical formula to calculate the pixel size or the voxel size. So FOV in the frequency direction divided by matrix, frequency matrix, the FOV in the phase direction and the frequency phase matrix in the slice thickness gives you the voxel size. No need to worry this mathematics. Actually, in the scan parameters or the scanner, you can see the pixel size directly. So if you want to increase the SNR, you can increase your voxel volume by adjusting the matrix, slice thickness, and FOV, and you can see how bigger is your pixel slice or how smaller is your pixel slice, and you can adjust your SNR. It's automatic, you can see over here. The matrix size, again, you can see the first image is 128 cross 128 matrix. It's isotropic or square matrix, we can say. The relative SNR is 1. I'm increasing the frequency phase matrix alone. So it's not a square matrix now, it's a rectangular FOV, rectangular matrix. SNR is reduced. And you can see the spatial resolution is improving a little bit. I increase the frequency matrix to 256. It's become isotropic or square voxels. SNR is reduced, but the spatial resolution is increased. So it's a balance between the SNR and the spatial resolution. An example with the higher matrix and with the lower matrix. So you can see the SNR is proportional to the reciprocal of square root of frequency matrix. So the larger matrix, the SNR is decreased. Smaller matrix, the SNR is increased. But the resolution in the frequency matrix will be improved. Overall spatial resolution also increased. The same thing will happen in the phase matrix as well. So this is with the 512 matrix, 512 into 512 matrix. And over here you can see this is 192 plus 192. It is also proportional to the 1/5 square root of phase and encoding matrix. So larger matrix, our voxel volume is less number of protons, and the smaller matrix, voxel volume is longer, and the SNR is less. Of course, the scan time will reduce if you are reducing your phase matrix, and since you are increasing your phase matrix, the scan time will be longer. So again, two examples, one with lesser matrix. Here you can see it is 256 cross 182, and the second image with the higher matrix. So you can easily appreciate, no need to explain in this image what's happening is you are increasing your matrix. It is clear. So what's happening with the slice thickness and FOV? I change both parameters. So since you can see here, the first image with the 18 centimeter of FOV with 5 mm slice thickness, I reduced the slice thickness into 3 mm. What happened? My relative SNR is reduced to 0.61. To gaining the FOV, to gain the SNR, I slightly increasing the FOV. So instead of 18, I increased a little bit of FOV. So I gained some of the SNR by changing these parameters. So altogether, the relative SNR is almost same, only 0.2% difference. This image is, you can see there is not much SNR difference. There is not much linearness. Spatial resolution is not affected much because I reduced the slice thickness, and I am keeping the same SNR, almost same SNR with this. Let's see, the same scenario, I reduce my matrix and I increase my mix. So in the first image, the slice thickness is 5, reduced to 3 mm. I lose some of my SNR and I reduce my matrix to 192 from 256. Slightly I gain a little bit of SNR and I increase my next. So what's happening? The SNR is almost same again. So the relative SNR was 1 in this setup and I reduce the slice thickness and I keep the same FOV. I'm not changing my FOV. And I increase the next. It helps to regain my lost SNR. The next is one of the options to increase your SNR without losing the spatial resolution. So the SNR and the receiver bandwidth. The receiver bandwidth, we can say that it's a range of frequencies what we are acquiring during the readout gradient. So it is the intensity of the gradient magnetic field of the frequency encoding direction. So it is only the one parameters, it's only the parameters, it does not affect the spatial resolution because I am not changing my frequency matrix, I am not changing anything that affects the spatial resolution. So I am just reducing the receiver bandwidth. Again, the SNR. The SNR is again proportional to the reciprocal of square root of receiver bandwidth. So in this chart you can see if you are reducing your bandwidth, the SNR is increasing, and if you are increasing your bandwidth, SNR is reducing. There are some other changes also happening with these adjustments. You can see one more new name called the minimum TE and the chemical shift artifacts. So what will happen? We'll just discuss what will happen if you change the receiver bandwidth, what will happen to the chemical shift. Okay. So here, I am not changing any parameters, I am just increasing my receiver bandwidth from 31 kHz to 62.5 kHz. Here you can see the signal is same. You can this box, this amplitude, the signal is same, and here also the same. But the baseline noise is more in the higher bandwidth. So here you can see the noise, yes, but over here the noise is more. So that's fine. If you are increasing your receiver bandwidth, SNR is reducing. We are getting some advantages by increasing the bandwidth. That means if you are increasing your receiving bandwidth, you can minimize your minimum TE. That will help to remove some of the susceptibility artifacts from your EPA based sequences like diffusion or brain perfusion imaging, fMRI imaging. It also helps to eliminate the chemical shift artifacts. We'll see how it is eliminating. So what is chemical shift artifacts? Just assume there is fat and the water protons in the same voxel or same anatomical location. So we know that the fat and water resisting with the different frequencies. It is increasing with the magnetic field strength because it is proportional to the Lambda frequency again. What will happen actually? So this is a schematic diagram of kidneys. Here, with the water protons surrounding by the fat protons. So the fat and the water protons resist with different frequencies or the precision of frequencies. The frequency, the fat frequency may shift and it may appear a dark rim artifact, something like this, on the image. It's called the chemical shift artifacts. So there are two different types of chemical shift artifacts again. This is we can say is a type 1 chemical shift artifacts. So I'm not going very deep into the artifact section. My colleague will take deep. So the type 2 chemical artifacts we can say in the dual echo imaging. In phase and out of phase imaging. In the out of phase imaging, we can see the dark rim artifacts in the organs. It's also called the India ink artifact or tape reconstruct artifacts. So this is one of the artifacts which comes only in the frequency direction. So to eliminating these artifacts, one method is to increase your bandwidth, receiving bandwidth. There is one more way to eliminate this artifact. You can use fat suppression. Simple way. So the whole fat will suppress and there won't be any fat water swapping or fat water shift. There won't be any presence of frequency difference again. So increase your receiver bandwidth or use fat set techniques. And you can do one more thing. You can shift the artifact location. You can change where you want to see the artifacts, whether you have to shift from right to left or you can shift from superior to inferior. That you can change during protocol optimization. Okay. So here you can see the bandwidth pixel option also. This is helps to setting the protocol as minimum pixel shift during the protocol optimization. Some of the clinical examples over here you can see this is 16 kilohertz receiving bandwidth. The frequency direction is inferior to superior. Over here you can see there is a dark rim in the receiver of bone. This is the chemical shift artifacts. Over here you can see it is bandwidth is higher, almost doubles, but artifact also eliminated drastically. Again, example of the wrist joint. Different methods with three different receiving bandwidths. So as you can see clearly, the receiving bandwidth increases, the chemical shift artifact also reduced. So said earlier, the chemical shift artifact is increased in the frequency and the mercury is increasing. So keep in mind that if you are working in a 3 Tesla scanner, you always keep higher or wider receiving bandwidth to minimize the effect of chemical shift. Reduction the SLR is not that in a high Tesla scanner. Clear that if you are compared to 150 and a 3 Tesla scanner, SNR increase almost 40%. So I apologize, there is an issue with the network. Okay, is it clear? Okay, so as you are increasing your receiver bandwidth, you can see the chemical shift artifact is reducing. Okay, SNR and next. I think this already knows, everybody knows that as you are increasing your necks, SNR also increasing. But actually what is happening? So the SNR is proportional to the square root of necks. It's not a direct proportion. So as you see in this picture, you can see I increase the necks from 2 to 4. My SNR, again, it's not a huge difference. It's SNR increased from 1 to 1.4. Not a huge difference from switching in the necks from 2 to 4. But the scan time will increase. And the appearance of a motion artifact also will reduce because the signal will be average and there won't be much motion artifacts in the image. This example you can see here with less necks, the motion artifacts are more prominent on the image. Higher necks, you can see the artifact also average and final image, there's not much motion artifacts. Here you can see the scan time versus the necks, it is almost doubles. But it is not directly proportional. SNR from 2 to 4, the SNR increment is just 40%. The scan doubles. Okay, so another cause. So the SNR is also depends which coil we are using. It also depends how we are positioning the coil. For example, you can say, if you are imagining a spine, so we are using only the posterior array coil. Some doctors will refer spinning of pelvis or any other region. So some texts, in my few texts, they are using the attached body coil instead of phased array coil, or the same phased array coil for imaging the pelvis or other anatomical region. That means, if you are not using the proper coil, won't get better SNR. Keep in mind that always use the proper coil for a proper anatomy. Okay, so we just discussed about all the spatial resolution part and SNR, the scan time, how it is affecting the images. Now let's discuss about the contrast weighting. So we all are heard about T1 weighting, T2 weighting in the PD weighted images. Okay, here, for a better understanding, you can see there's a short TE, long TE over here, and the short TR versus long TR. So short TE, short TR, we will get T1 weighted images. Long TE, long TR, T2 weighted images. And short TE with long TR will get PD. Let's see what is this TE and TR and the flip angle, how it is affecting your signal. Okay, so this is a simple spin echo pulse sequence diagram. So initially there is a 90-degree RF pulse followed by a 180-degree rephasing. After some time, we are receiving. That means our TE. The TE from the 90-degree RF, initial RF, and at what time we are receiving the signal. That is T. TR from the first 90-degree RF and the second 90-degree RF. Let's see what's happening if you are increase or if you are reducing TR. Okay. If you want to get a good signal, you can see the z-axis is the longitudinal magnetization and the xy axis is the transverse magnetization. If we want to get a very good SNR or very good signal from the protons, all the protons has to be in the transverse magnetization. What happened? The shorter TR. With a very short TR, maybe some of the protons may not be in the transverse plane. The next 90-degree echo, some protons may not completely dephase and in the longitudinal plane. The next 90-degree echo, the protons, less number of protons will go to the transverse plane. So shorter TR will reduce the signal or it will reduce the SNR. If I keep on increasing the TR, what happened? Most of all the protons will be the longitudinal plane. But all the protons will be in the longitudinal plane. And after the next TR, it goes to transverse plane. That means all protons in the transverse plane and you are getting a good signal. The longer TR, your SNR will be higher. Shorter TR, SNR will be lesser. One example I can say, we know that T1 weighted images with shorter TR. Sometime back I have a query from one of my customer saying the T1 fat set images and the T1 images are very grainy. So I just look at the parameters. The tags are reducing the TR like 200, 150 to reduce the scan time. Yes, we know that. If you're reducing the TR, scan time will reduce. But what happened? Finally, your images are very grainy because your SNR is very poor. You're using very short TR. So it is very important to use the appropriate TR for an upperly weighted contrast. The TR range for a T1 weighted images in a 1.5T scanner, 400 to 800. For a T2 weighted images, it is, we know that is longer, 2000 plus. So if you are reducing in these levels, you will lose your SNR. Ultimately, the image may not be diagnostic and you know that.
Repetition.
Okay, so next, TE. Okay, again, short TE versus long TE. So with the shorter TE, after the transverse magnetization, a lot shorter time we acquire the signal. What happened? All the protons are in phase and all the protons are in the transverse magnetization. It's produced a good amount of signal. That means shorter TE gives good signal or SNR is higher. So what's happened? If you increase your TE, you know that after some times the protons will start to dephasing. So, then sometimes the protons are already go back to the longitudinal magnetization. There won't be much protons to produce the MR signal for you. That means longer TE, your SNR is less, the signal is less. Okay. So what's happening with the flip angle? If you are altering the flip angle, what's happening? So we already discussed about the good signal or the high signal is coming from the protons or the transverse plane. In this example, this is only 10 degrees. This proton is tilted only 10 degrees. The second image, the proton is tilted only 45 degrees. And the third image, the proton is completely tilted 90 degree and all in the transverse magnetization and produce good signal. That means low TE, less signal. Low TE, it gives better signal. That means your SNR is higher. We discussed already short TE, less SNR, long TR, high SNR. Calculate the flip angle. shorter flip angle, lower SNR, longer flip angle, better the SNR. So what is fast spin echo? What's happening? So in the previous couple of slides, we discussed only about a single echo. 190, 180, then we are receiving the echo. What's happening? If you are increasing our 180 degree pulses after the 90 degree, in this case, we are giving 8 180 degree RFs after the first 90 degree RF. Simultaneously, we can see we have 8 different echoes with different amplitudes. Okay. So instead of 180, we are giving 8 180 in this case.
Time of echoes.
So we can say the echo train length is 8. Or simply the ETL means the number of 180 degree RF pulses after your 90 degree RF. Or the echo train length. So what's happening if you are increasing your echo train length? What's happening? Your weightage of your image, or what happened with your scan 10 and the parameters. In this image, you can see the maximum signal is coming around the fifth 180 degree, after the fifth 180 degree. That means the effective TE is almost somewhere over here, right? So instead of 8, I increase the echo training to 20, for example. So that means we have a 20 different echoes with different signal amplitude. What happened? My effective TE is longer. The long TE means it's going to be T2 weightage. There won't be any T1 content in that image. There are some trade-off for the ETL and the scan time. We'll see. What happened if you are increasing the ETL? Your T2 contrast is increased. We know that effective TE is increasing. That means your T2 contrast is increasing. Number of slices is reducing. So accommodating all the slices, we are increasing the width of the echoes. Scan time is reduced. We know that in a single multiple 180 degree RFs, multiple lanes of K space will fill and the scan time will reduce. The motion artifacts will increase. Yes, the motion artifact will increase because there is a chance of moving the protons in between these 180 degree RFs. It will ultimately cause motion artifacts. And the edge blurring, that also can happen with longer ETLs. So for longer ETLs, echo train lengths, what happened is the protons, there's a chance of protons are dephasing. And we know that the phase damping in the K space is depending on the MR signal. If you are increasing the ETL or if the protons are in different phases, it may place in a different areas in the K space level, ultimately gives the edge blurring on the images. So this is the trade-offs of the ETL. So keep in mind that if you want a T2 weighted images, you can increase your ETL. For a proton density weighted images, you can keep an ETL of 6 to say 10 maximum. For a T1 weighted images, ETL has to be even lower, maximum 4 or 5 for T1 weighted images. So you should not increase your ETL more than 5 for a T1 weighted images because your T1 property is reducing. Especially I have seen some cases with T1 weighted images with ETL of 16. What's happening actually? There is no T1 content. Just imagine if you're giving contrast and run with the same parameters, sometimes you may not see any lesions. For the contrast enhancement, you may not see because there is no T1 content. Okay. If you are seeing the factors affecting the parameters affecting the SNR and the things. Now we come to the imaging options. So the imaging options are the additional features or the functionalities to the image processing. It can help to control your motion. Some imaging options can help to remove some sort of artifacts, and you can increase your spatial resolution and alter the imaging contrast. Okay, this is the user interference of a GE scanner, and over here you can see the imaging options. So if you click on the imaging options, you can see the whole list of imaging options. The options which is compatible in that particular PSD are active. It's not meant for that particular PSD, it won't be seen in the imaging options. So I can say that this is the complete list of imaging options, but in some imaging options, some PSDs, some parameters, some protocols, we cannot see the whole list. In the MR image, imaging parameter options, you can see in the parameter screen on the left lower corner, last. So this is your imaging options, or in this case, on this particular image, all these imaging options are active. FC, flow compensation in the frequency direction. So spatial saturation, A means anteriorly placed saturation band. No phase trap is active, EDR and few other. So this you can see imaging options used, what are the imaging options are used. Suppose if you are faced with some image artifacts and you are getting some image artifacts and you are sending the images to the application guy, to make sure that you include the whole picture or the whole image, so the apps guy can see what all the imaging options are used in that particular scan, and we can help to eliminate that artifacts to switch on or to activate imaging options. We will discuss briefly about some of the imaging options. Anyway, the list is too long and I cannot complete the whole list in this limited time. However, I can complete the most frequently used imaging options and how to improve your image contrast and eliminate the artifacts. Okay, the first one is flow compensation. Flow compensation, or it will be mentioned as FC in the image. So it is uses to correct the phase of the flowing nuclei in the image to eliminate the artifacts from a flowing or moving protons. Example, in this image, you can see a dark bands over here. So this is the flow artifacts from the moving CSF. Similarly, we will get some artifacts from the arteries, or we can get some artifacts from the veins. Any moving nucleus. Why these artifacts are coming? So the stationary tissues are experiencing, or the stationary tissues, or the phase coherence, or all protons are in phase, we can say. So the flowing nucleus, the phase are different than the stationary tissue. So what the flow compensation gradient are doing is, it's trying to uniform the phase with the stationary tissue. So you won't get any flow related artifacts. So simply you go to the imaging option tab and you can switch on the flow compensation. it will ask you in which direction the flow artifact has to be compensated. Means you can compensate in the frequency direction or you can compensate phase direction. That's a user choice. Okay, so in this image you can see there is no flow related artifacts. There is the CSF is brighter, no defects, but with flow compensation off, you can see there is a dark line artifacts. Okay, two images. In the second image is a C-span image with the CSO. So keep in mind that always all these ghosting, all these flow related artifacts are presented coming from this direction. Because the flowing plates, the phase is during the phase and flowing steps. Signals. What will happen is your frequency direction or the sledge direction, phase direction has to be balanced. In this case, you can see the superior to inferior. Apply the phase the same direction, that means it's superior direction. In two ways you can apply certain phase. You can apply sideways. But phase has to be the direction of the flow. Yes, you can activate the flow compensation also. Also, there are one more method. Spatial saturation above is another. We'll see what is spatial saturation. So the saturation band is a simple 90-degree RF pulse. It is applying just before the second 90 degree. It can suppress the movement or suppress the issues which is causing. In this case, you can see it's a lumbar spine image placed in saturation band anteriorly. So the respiratory artifacts, the peristalsis, the intestine can be suppressed placing the saturation band. So there are three types of saturation bands. One you can place inside the FOV. One you can place above, outside the FOV, inside, inside. And one is concatenate that means for walking sap or moving sap. So since your slices are moving, the sap band also will move forward. That is used for cooling off angiographic techniques. Okay. So in this example, you can see there is a flow-related artifacts from the aorta. So simply placing a saturation band superior and inferior. So the spatial saturation band you can see over here. So you can see the superior saturation band is activated.
यहाँ पे बैठ पापा पढ़ाई कर रहे हैं।
Okay. So in the advanced tab, there is an option increase the saturation. which you can suppress the three types of suppression. It's a light suppression, medium suppression, and strong suppression. Okay, three images with three options. The images are window wider to see the saturation point, where the saturation point is placed. So in the first image, you can see the tissue is suppressed by the used the light. The second image, medium suppression, then the third image, strong suppression. But this image enabled by simply take the number advanced 10 patients sample. If you want more suppression, you make it 1 or 2. Alright. Morning navigator or simply the navigator. So we know that the motion is always a lot of movement effects, especially the moving anatomies. Just imagine we are doing a different scans. Because of the respiration. Okay, how do you make it? You can use the navigator pulse, or you can check the diaphragmatic movement. The navigator aim at the artifacts. So it will synchronize with your acquisition, and it will start, or it begins acquire the data once it is in end expiration. But once it is an expiration, position starts. It starts expiration, position starts. So the navigator has to be placed in the right, has to be placed well. Don't worry. The navigator placement is perfect. Answer. Just right click. You have an option. Select the navigator. Just submit. And from the toolbar, three clicks. The navigator is placed. Recommendation, I can say that during the conference, you should not be your shoulder.
ठीक है
The shoulder zone anatomy.
पापा को पढ़ाई करने दे हाँ यहाँ पे बैठना है हाँ तो पापा को पढ़ाई करने दे ठीक है
Suppose
पढ़ाई करने दे पापा तेरे को मैं ध्यान रखूँगा कॉपी देनी है तेरे पेन का दे दो इधर ले बिस्कुट नहीं खाना तुझे नहीं देते यहाँ पे बैठ के खा यहाँ पे
you can see every Mama.
मैं बिस्किट दे दूँ तेरे साथ हाँ किसने फेंके
क्या करनी बेटा इधर या कर
पापा पढ़ाई कर रहे हैं ना तब बस खाली दे
We talk about the motion.
पापा दे दो
So people are thinking about how to reduce the scanning time will be the movement effects.
यहाँ पे पापा को पढ़ाई करने दे हाँ पापा को
In
मत
last
कर
scan,
ठीक
you
है
know that this takes common sequences. So you can reduce the scan time. Especially for the company. So we call it as parallel imaging techniques to speed up your scan, reducing the scan. You have two options. One is a
Papa, Papa.
Papa
को पढ़ाई करने दे दो आपको ही काम किया रहने दो उसे
So as a sensitivity and putting technique, we need to have an oil sensitivity map. So it requires a calculation again before
बस
the calculation
बैठ जाओ
it will
इधर
correct
यहाँ पे बैठ हाँ ये इधर
oil sensitivity, the signal,
तब तो फिर भगवान जी
and
को
every alternating space it will
यहाँ पे
correct. So this can be half. Here you can see the 60 seconds. 8 seconds. A set factor of that is if you can have it. Here the limit can reduce or skip. Here the limit can reduce or skip. The arc for data-driven telemetry technique. There is auto-calculating reconstruction for that distribution. So it is a 3D kernel technique for the data used for all the three texts, all the three-dimensional technique to use the scanner. So what it does is it's oversam the central casements and undersamples the outer casements, and the missing line of outer casements is taking the lines from the neighboring points, neighboring lines. So we have a contrast because the whole of the excess so this is a data-driven or case-based limits. It doesn't require any calibrations. Keep in mind that if you are using any parallel imaging technique, if you are increase the acceleration factor, you are reducing your SNR. Okay, so no phase wrap. So this is again one of common artifacts. I mean, knows how to eliminate these artifacts. Just stone the no phase wrap option or increasing your oversampling option. So how this artifact? Why this posterior? Suppose it's a brain imaging. Why this posterior anatomy is coming anterior and this anatomy coming here? Okay, so this is a phase encoding curve 0 to 360 the phase encoding. And assume this is abdominal imaging and this is your FOE, right? So you can see this phase area and this area, it's the same phase. But the scanner or the system now differentiate it only knows where is the frequency. Okay, there is issue with the network. For that. what it does is it will just increase your overall FOV, and it doubles the phase or sampling. So there is a flexible no phase type option, so you need to actually double your FOV or you actually increase over sample. So as you can see that the coil sensitivity area is here. The signal is less over here, so you don't need to use a full oversampling factor or 100 dB. Okay, so you can change in the increment of 1.1 or 1.2 or 1.4 something like that.
Can you share the presentation again? Hello?
Can you hear me? Hello? Okay. So we can I apologize for the network issues. Okay, so we can increase the oversampling factor is increment of 1.1 or 1.2. Like that, and you can completely avoid the FOV outside the imaging volume which is coming inside your actual display FOV. Okay, so we have another option called the matrix zero field interpolation to increase your apparent resolution. Suppose if you are scanning
ये मैं यहाँ रखी मेरे मटका
बस चिपड़ होता
yeah, now you can hear what on the screen. Okay.
Can you hear me now?
Oh, can you hear me now?
Hello?
Can you hear me? Okay.